Welcome to Winning Edge. Today's topic is D and F block elements. Importance of D and F block elements in modern world can be understood from a very simple fact that without these elements we can't imagine all the technological developments that we have achieved today. Let it be our steel industry, which is basically iron alloy or gold, or let's talk about the alloys that we use in our aircraft industries. We're having a very high strength, like titanium alloys, or let's consider the use of D block elements or F block elements as a catalyst to produce commercial products at affordable prices. Or may talk about plating of essential components with nickel, which will give it a corrosion resistance, or use of copper for illuminating our modern society. Copper, because of its good conductivity, is used for distribution of electricity, or use of these alloys as a cutting and grinding tools. We have these elements humongous role in modern day civilization. So let's try to understand some important characteristics and behavior of D and F block elements. First, this lies in the middle of periodic table. The first element in D block elements is scandium. The very name given to these D block elements as transition elements, because while going from S block elements to P block element, we have to pass through or transit through D block. General electronic configuration of these elements is n-1, n here is principal quantum number, and electronic configuration in d orbital will vary from 1 to 10, and in s orbital varies from 1 to 2. This is general electronic configuration for D block or transition elements. Transition elements, technically defined as the one which has incompletely filled D orbital in its ground state or in any one of its oxidation states. So group 12 elements, this is known group 12 elements which having a completely filled D orbital. So technically we can't call them D block elements, but for convenient part, for the purpose of convenience, these 12th group elements are kept with the D block only. All the transition elements display typical metallic properties such as high tensile strength. Tensile strength means it will not break when it undergoes a stress. Ductility means they are ductile, we can make them in form of sheets. Malleability we can draw them into wires. High thermal and electrical conductivity. Heat and electricity can easily pass through these metals and they have metallic luster. In simple terms, we can say D block elements having a typical metallic properties. Let's take first 3D series. This is a 3D period element. First D block series 3D. So when what happens, 21st element scandium, first electron goes to d orbital. In titanium, 2 electrons will half fill the 2d orbitals. Vanadium, 3 electrons fill it up. And in chromium, we will having 4 unpaired electrons, and here is a 2 4s electrons. But what happens? 1 electron from chromium 4s orbital shifts to 3d orbital to make it half filled. The reason is this exchange energy in 3d orbital for after filling it having a greater stability, because it turns out to be half filled electronic state, which we know having a better stability, and the energy required for unpairing it is compensated by the stability required by half filled electronic state. That is the reason 1 electron will promote to 5th d orbital. It is a special electronic configuration 3d5 4s1 for chromium. Next element is again mag. Here what happens? The 1 electron will pairs it up. So we having a 3d5 half-filled electron configuration. In iron, pairing starts up. Cobalt, 2 electrons pair up. In nickel, 3 orbitals will having a completely filled or having a 2 electrons. In copper, we face the same situation like we faced in chromium. We having a 1 unpaired electron, and here s orbital having 2 electron. We know fully filled d orbital having a greater stability compared to a deficient d orbital. That's the reason 1 electron will promote to make a 3d10 and 4s1. This is a general electron configuration for copper. In zinc again, we having a fully filled 4s and d orbital. This is all about 3D series. Now, in the transition metals, exception to zinc, cadmium and mercury, they are very hard and having a high melting and boiling points means they have a low volatility. Here on y-axis we having the melting points which is in thousands Kelvin. Here in x-axis we measure atomic number. Let's start with 3D series. Titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper. And then we have it here again. Next series goes up to silver. And 5D, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, and finally gold. So what we see here is melting points. First observation is as we keep on increasing the atomic numbers from 3D series, 4D series, 5D series, melting points in general will increase from that one D block element to the other D block element to the next D block elements. This is the first general observation. Next, across the period in each D block series, we see first it increases, drops down a bit, and manganese, then it again increases and start decreasing in the end again. The high melting points of these metals are attributed to the involvement of greater number of electrons from the d orbitals in addition to the ns electrons for interatomic bonding. Because of their better interatomic bonding, they have stronger bonds and high melting points. In general, this is true for d block elements. And the next point, not only s orbitals but d orbitals having a greater number of electrons that are available for interatomic bonding, that makes the melting point in general higher. Now, in NEET series, we see melting points of these metals rises to a maximum, like in chromium here, at D5 when we having a half-filled or unpaired electrons. That's true for chromium, molybdenum, tungsten without exception. This is true for all these elements. All these having a D5 electronic configuration, and they are having the highest melting point in each series. It means we can make it out. Greater number of unpaired electrons availability is responsible for stronger interatomic bonds between the atoms of these elements and making their melting points high. That is the reason, like, we have applications, we use titanium in high-end applications like aircrafts, defense aircrafts, and chromium is used, for plating bikes like HD. We already discussed. The maxima in each series occurs for element having greatest number of unpaired electrons. So, one unpaired electron for each orbital is particularly favorable for strong interatomic interactions. That we see here: molybdenum, tungsten, chromium. D5, which is half-filled. Next is enthalpy of atomization. Conventional elements exhibit higher enthalpies of atomization because of the large number of unpaired electrons in the atoms. They have stronger interatomic interaction that we already saw, hence stronger bonds, and it's not easy to break. This is enthalpy of atomization for 3D series, 4D series and 5D series, and we saw a great degree of similarity in all the series. Again, like melting point, first it increases, then it starts decreasing with a reduction in number of available unpaired electrons.